So this video is just a YouTube version of the talk I gave a couple of weekends ago at the Singapore DevFest. The idea is to explain how you can better prompt or fine-tune a model based on lessons that have been learned from reinforcement learning of LLMs, which has been the whole theme of this year. I'm not going to do a deep dive on the literature behind reinforcement learning, but I will be talking about the takeaways that people who've been doing reinforcement learning or teaching reasoning to LLMs can bring to regular prompting and fine-tuning. So first off, I'll be talking about the different phases of training. Now, while this may be a recap to some of you, even if you haven't seen this before, I'll be doing it in an opinionated way so you can see where all of this is coming from. The second piece will be some of the lessons that can be taken away from the reinforcement learning work that people have been doing with these models. Thirdly, I'll then refocus on how can we benefit from these takeaways, in particular for fine-tuning and prompting models. And then I'll wrap it all up. Okay, for the phases of training, basically I'll be laying some foundations. Now, typically the most expensive part of training is this pre-training phase, where we're going to be using multiple trillions of tokens, huge data, huge compute. So on the right-hand side is an illustration of what's going on. Suppose we find from the vast training set the sentence, "the cat sat on the mat." Basically, I'll tell the model that it needs to predict the next word for each of these tokens. And I can do this by putting "the cat sat on the mat" in at the bottom and "the cat sat on the mat" but shifted over by one at the top. So for each column, the model will learn how to go from, for instance, the word sat to the word on, or the word the to the word mat in this example, based upon the history. Now, the sneaky thing about these transformers is that because I can mask out all of the history at each column, I can only make it look backwards. I can train this whole thing in parallel. Basically, I can give it sentences or large blocks of text, and just by shifting it over one, I can train every single one of these columns to predict the next token. Now, what this does is create what's called a base large language model. And in particular, this is in a way untrained to do any specific task. It just knows from the wide distribution of everything it's seen on the internet how sentences are likely to continue. In particular, if we look at the word the here, sometimes the word the is followed by cat, sometimes it's followed by mat. Clearly, context is important, and these models learn not just for each sentence, but for every context, how many possible different other ways, the whole distribution of continuations. And so while it may be learning from individual examples, people tend to think of this as learning the distribution over all possible things that can be said. And these models tend to become very even-handed in terms of what humans are likely to say. So in a later phase of training, called fine-tuning, basically we move from trillions of tokens to thousands of examples, or maybe millions of examples, and we'll dial up the learning rate. Essentially, we're trying to insist that the model follows our pattern. We put in "the cat sat on the mat," we're going to say that this is the right answer. And basically, we're going to impose this kind of conditioning on these models. It's very similar to pre-training in a way, in the kind of parallel nature of it. On the other hand, because we're kind of intensely insisting that this is the right answer, people tend to put this in what's called post-training rather than pre-training. And this is what's going to create a fine-tuned LLM. This supervised fine-tuning is what people do to fine-tune an LLM. Now, once we've got a model which has been trained, maybe fine-tuned, we'll then want to do inference on it. So this is actually using the model, using it to predict phrases or sentences or the output. We can also apply a prompt to this, so we can fill in the context originally so that it can then continue for us. So suppose we had the input sentence, "the cat sat on the." We would hope that from the distribution of all possible words that the model could come out with, it would choose mat as being the most likely one, because that's kind of what we have in mind. But it could come up with any possible token. Now, people have a way of kind of filtering out like super unlikely tokens. But basically, it's going to pick out one of the top K or within the top P of tokens. Or if you're doing temperature equals 0, it'll pick out only the most likely token. but there will be some way of crystallizing the distribution at the top over all tokens into its choice, which will become its output. Now, the strange thing is, we haven't actually trained the model to do this task. In particular, while it does know about how the internet is distributed for all kind of contexts that are on the internet, it doesn't know how to respond to one of its own outputs. Now, suppose it was lucky and it comes out exactly with something already in the training, then it will be on track, it knows what to do. But as soon as it starts to deviate, it will be in an uncharted territory. It will be essentially making it up as it goes along. The key thing is that we haven't actually ever trained the model to make it up as it goes along. We've trained it to predict what a human would say in each situation. So essentially, the models are not trained for coping with their own output. This is kind of surprising. In fact, it's kind of surprising that this works at all. And back in the day, with GPT-2, for instance, people were very surprised that it could keep on subject for as long as it did. So this difference, while it may seem subtle, is actually quite important. So to make it so that LLMs can respond to their own outputs, people have been using reinforcement learning. Now, the earlier version of this was called reinforcement learning from human feedback. I won't go into that today. I'll be talking about essentially this year's reasoning style of reinforcement learning, this GRPO method, which was revealed to the world by DeepSeek in their paper of January 2025. The idea here is basically you're going to roll out lots and lots of potential completions, and the ones which are getting the right answer, because we're going to basically be using it for kind of maths questions, questions which have a concrete correct answer, we'll just let it reason, like do some thinking tokens, and if it gets the right answer, we're going to assume, okay, that reasoning is probably right because it got to the right answer. Now, the crucial difference here is the model is reacting to its own outputs. And one of the key things about the aha moment, which was seen in the DeepSeek paper, is basically the model essentially realized that it was kind of in control of its own output and that it could actually search down different paths for itself or do backtracking. This kind of reasoning was something more sophisticated than it would see in internet data. So one key thing here is that in response to a prompt, the model is coming out with a large number of its own completions, and it is then getting told which of those completions looks good and which are not very good. But crucially, it's being taught about its own outputs rather than being shown what somebody else would say. So in that sense, the model is now beginning to see the consequences of its own behavior and potentially modifying its own behavior so that it might be more on track or more correct in the end. So for the next part, I'm going to talk about some of the lessons to be learned from reinforcement learning, and in particular, some of the takeaways from a Gemini symposium, which was held in Singapore. So this symposium was an event primarily for research folk in Singapore, where an all-star cast of Google researchers explained some of the key directions that they had found interesting in the public literature, though they were very tight-lipped about what they were actually using internally for Gemini. So my takeaways here are both from the literature which I've read and from interpreting some of the things which they either said or didn't say. Any mistakes are my fault. It was a great event and it was good that Google held it in Singapore. So the first of my three takeaways are that base models, which are the result of pre-training an LLM on trillions of tokens taken from the internet and maybe some synthetic data, these models already probably know the answer if you let them do multiple completions. So if I roll it out 1,000 different times in response to the prompt, the true answer is probably in there somewhere. So one of the things which was almost unsaid by these researchers is that these base models, pre-trained only, have a very special role in the kind of ecosystem. One of the key things is that they're kind of pure in that they haven't been told specific points of view, they've been told all points of view, and they're somewhat unbiased in that they've seen the whole range of what humanity does to particular contexts. Now, this unbiasedness is not about, say, racial biasness, and these base models may have horrible stereotypes built in purely because that is what they see on the internet. This particular kind of unbiasedness I'm referring to is if you ask it the results of flipping a coin, it would say heads and tails in equal proportions. So given that they understand the distribution, all we have to do is ask them a lot and they will give us a fair selection of what people would say in response to the prompt. So the second of the three takeaways is that the consensus of these answers is likely correct. Now again, this isn't a statement about politics, this is more a statement about distributions and how probabilities work. So the sense in which this consensus works is that generally on the internet, people are right in the same kind of way, but wrong in lots of different kinds of ways. So suppose I'm asking a mathematical question for which there's one correct answer, but I don't actually know the correct answer. If I sample many outcomes from this reasoning model, it will come up with lots of different answers if it's making mistakes. But if it's making a correct reasoning path, these will all end up at a single answer. So in that sense, this kind of majority voting can be used to determine the correct answer, to essentially go for a self-improvement loop. Now, once the models have been fine-tuned to only give a particular answer, we've kind of bent them out of shape. This kind of begins to show why these base models have a special role. And the third point is that training off policy is bad for models. And I'm going to explain what off policy means. So this is going to get to the heart of advice for prompting and fine-tuning. So to explain what off policy means, of course I should explain what on policy is. On policy is whatever a model would come up with itself, left to its own devices. Off policy is where you have some output which the model didn't suggest, but you're telling it about. So off policy sequences of tokens are things that the model wouldn't naturally have said itself, and forcing the model to understand those or to say those is basically twisting the model a little bit. And we know that these base models are somewhat fragile, and as soon as you start twisting them in one direction, you may be undoing stuff in another place where you're not even looking. So this is a kind of a fragile aspect to training models. And if I'm insisting that a model does one thing, I don't actually know where I'm damaging it because I'm not looking at that. I'm really testing it. Did my training work? I don't know the other side of that, what did it unlearn when I got it to do my thing? Another aspect of this is if I'm instructing it to produce unexpected output, in some sense, I'm causing the model to be untrue to itself or kind of lying. And so this is kind of one of the behaviors which might cause models to hallucinate, and I'll explain why. Suppose I had a question where the true answer for the model is, I don't know. Hopefully the model would admit that, but suppose it would actually naturally admit something. And then I come along and say, okay, here's some more training data so that you do know. If you're ever asked this question, here is the answer. And so now the model is conditioned as soon as it comes up with this question to give this answer. Now the model can learn that in two ways, one of which it will just associate the context with exactly the right answer. Our job is done, that was well trained. Another aspect is if it gets a question where the answer is I don't know, it should come up with an answer which isn't I don't know. You're telling it that an answer exists instead of I don't know. So in response to this training example, where you're telling it the fact that it needs to come up with, the model can learn this in two ways, one of which is to understand the flow between the context and the fact. And another, potentially simpler way, is if it's uncertain, it should just blurt out facts. You provided one for your particular situation, but maybe it will just invent other facts. And so this kind of gives some hint as to why training on facts may not be a great idea, because the model might learn the facts, but it may also short-circuit what you're doing and produce hallucinations for other questions. Okay, so now let's take the RL lessons and see how we can benefit from them. This is in three parts, the first of which is about getting on policy. So as I mentioned before, on policy means that the model is going to behave in a way which comes naturally to it. And so here we're going to see that the model will actually actively try and tell you how it was trained And I'm just saying we've got to listen to that, because keeping the model on policy is going to give us better results than to try and impose our own thinking onto it. So let's move on to prompting with some examples. So for prompting, basically the on-policy idea suggests that we should be prompting in a style that matches the LLM's training data. Now, the LLM will have seen many things on the internet, but one way to find out how it wants to think about a problem is to ask the model to explain the problem back to you. So our first steps might be to explain the problem to the model, but get it to reply back with how it sees the problem, because how it sees the situation is very telling about what it knows and what it doesn't know, and that would allow us to prompt it much more in line with its training. So here's a concrete example. Suppose I had a kind of a vision model which I wanted to extract some bounding boxes from. Now, a bad version of prompting this would be, give me bounding boxes in a format XY HW using millimeters within the A4 page. Right? This is a very clear instruction, but this may not be what the model wants. So a better version of this would be, give me the bounding box information for objects in the image. So here we're not specifying anything about how we want the bounding box information delivered. We're keeping it very loose. Okay, now once it's given you some output, you say, explain what those numbers or labels mean. So again, keeping all of this in context, you'll then ask, describe a suitable data structure for the above. We're not expecting any particular computer language or anything. We want to understand what data structures it uses for bounding boxes. And it's already started to explain the different details. Now, once it's given you a format which it likes for bounding boxes, but in its own words, you say, okay, give me the bounding boxes in that format. And then once you've got that format from it, which you can be pretty sure it's been trained on now, you then post-process this using code. So we don't force the LLM to do any calculations. We just encourage it to do as its training has suggested, and then post-process it to whatever dimensions or measurements we need. Hopefully you can see we've kind of teased out how the model was trained from the model, and then just asked it the natural question so that it can behave in line with its own training data. So here's another example for extracting a marketing persona. The obvious prompt might be, fill in the following XYZ persona profile, where you give a whole bunch of categories that the persona has to identify with for this marketing persona, where this is a document which has been designed by a committee. It might have lots of in-house jargon. It may have some special twists and turns about things which could and couldn't be valid for personas. This is imposing a lot of your stuff on the LLM. Let's see how we can charm it out of the LLM. So the better version, I would suggest, is we ask the LLM what it thinks a marketing persona is. So you may think that the LLMs may be good at code, but may not have a good grasp of what a marketing persona is. But naturally, these LLMs have not just read one book about personas, they've read all the books about personas. They've read about personas in all different directions, in terms of marketing or UI or all these other things. LLMs will have a very detailed knowledge of what persona is. They don't know what you mean about it, though. So our first comment is, explain what a marketing persona is to the LLM, and it will come up with a whole array of different things which it impressions. Then you say, okay, describe profile items relevant for marketing personas. So now we're trying to nail it down a bit, like pick out some key categories and some key qualities that you look for in a marketing persona. Okay. Again, this is the model's output. Then you say, okay, create a data structure and a rubric for measuring each of these items. So here we're kind of getting it to, it's already come up with how it feels about these different things and also the things it's looking for. Now we're telling it to now give a rubric for how to define each of these things and also a data structure into which to fit the information. So this, in a way, is making it more similar to the bounding boxes idea. We're getting it to essentially put itself in a situation where it's been in control of a lot of the terminology here. Then we're going to say, using this rubric. So here we can actually copy the rubric that it's come up with into a new chat window, whereas before we've been essentially piling on from one thing to the next. When you're developing this, I would suggest do this all in one chat window. Eventually we'll move the rubric over to a new one to condense the prompt out a bit. Okay, so using its own rubric, fill in its own data structure that it just suggested, and you may provide it some additional context, maybe some examples. And then as a final step, you would say, using this data structure, which it just came up with itself, populate my persona profile. And so here, the LLM, its job is just to fill in your form, but from data which is it's come up with, which has been basically on target in terms of how it thinks about these marketing personas. Now, if you find it needs a bit of course correction, of course you can go back and ask it again in a slightly different way, or just ask it again and see the difference in responses you're getting until you hit on one which is okay. It probably has within it a good grasp of what your marketing department wants to have in there. So you can just wait it out until it comes up with its own explanation of what you're actually doing. But by doing these steps, you're now focusing on what the LLM naturally wants to do and then filling in your form as a last step. Now, if you're interested in this kind of automated prompting idea, I would point you towards something called JEPA, which is part of the DSPY framework. Basically, this framework allows you to treat the prompts as something which the LLM is able to alter and optimize itself. So you or your developer team could give it a bunch of known responses, but you could allow the prompt to be updated until it matches those responses as much as possible. And this is a way of automating this. So I'm not going to get into this in this video, but leaving this here so that if you want a pointer to how to take this to the next level, there's something to go on. Okay, so now let's look at fine-tuning. So suppose I'm doing supervised fine-tuning of facts. These facts aren't going to be on policy. So we've got a fundamental problem with teaching new facts to an LLM. Maybe the answer here is to use some retrieval augmented generation. So you put the facts in some kind of database and get it to look up facts it doesn't know. That would be a very valid way of avoiding training the model to essentially lie when it doesn't know things. Another idea would be to use a system prompt. If you've only got a very few number of facts, you could put those facts in the system prompt so that it can refer back to its own context. And this is something which models will be very familiar with, will be entirely on policy. As with the RAG use case, because nowadays people have been teaching them a lot about search. Now, as an alternative idea, supposing you've got someone insisting that you fine-tune a model on these facts, what you could do is add a special context. Now, suppose you're at company ABC, you might put hashtag company ABC, as that would be a special context. That sequence of tokens could be your special context. So what you could then do is add that as part of the prompt for all of your training or all of your new kind of factual training. Now, what this would allow the model to do would be to attach the facts not only to the context, but also your special context. So in some sense, this special context creates space for new facts, which won't disturb its general knowledge when that special context isn't present. But the special context, which you could then put in your system prompt, would allow it to come up with this additional stuff from some thinking space, which is distinct from other facts it would know. So the idea here is rather than crush its general knowledge, which you would do in a way where you couldn't even know how you're harming the model, you give the model space to remember these new facts well away from the I don't know responses or other things that it's been so carefully trained on already. Now, if we move away from facts to kind of behaviors for fine-tuning, what it might be nice to do is use the model to regenerate your data. So suppose we have a data set of how we want the model to respond in certain circumstances. What we could do is get the model to restate the situation, essentially how to prompt itself for each of these. In some sense, we're generating synthetic versions of our data set. Now, synthetic data has been like a huge topic, You might say, well, I'll use a big LLM to do that. I can generate synthetic data for very cheap. But here we'd say, no, what we really care about is we want the synthetic data to be on policy for our model as much as possible. We can't use a big LLM to generate data for our model. We have to make our model come up with its own training examples. Another thing we could do is to get it to generate additional training data using the same model. For instance, we could do relationship reversals. So this is to handle a common issue with LLMs where it may know who Tom Cruise's mother is, but if you ask it, who's that person's son, it wouldn't know as Tom Cruise. So this kind of reversal thing, by restating the fact which you have once in your training data, synthetically in lots of different ways, you'll be able to fix up semantic holes in the LLM's understanding of the topic by having these synthetic training examples. Again, the important thing here is to get the model you're targeting to produce these examples so that when you're reinforcing them, essentially by saying, okay, this is how you should be phrasing it, you're not making it go completely off track compared to what it would have said before. You're just reiterating that this is the right thing to say. Okay, to wrap up. So first off, we looked at the phases of training and saw how the base models and fine-tuned models have actually been trained to do a task which is different from what we actually see in practice, where we're rolling out a sequence of tokens from the model and it's having to continue that. So knowing the distribution of what the internet would say after each word is rather different from coming up with a word and then responding to your own output again and again, which is how rollouts work or how chat works when we actually do inference with these models. Hopefully the takeaways I explained from reinforcement learning as applied to prompting and fine-tuning give you a feeling of how understanding kind of researcher vibes can lead you to better results, even if you're not going to be reinforcement learning training models yourself. To see what researchers are finding out about these models as the field progresses, that vibe check can be very useful applying to your own work. And so finally, one of the key takeaways is I would encourage you to become a model whisperer. Learn how to talk to models and then use what they say. Be a good listener in terms of a conversation with a model, because it is really trying to tell you how you should be prompting it in order to get the best results from it. Now, you might say, surely a really good model shouldn't care how I talk to it. It should essentially understand what I mean and just come up with the right answer. Well, maybe that's what's happening with these thinking models. The big, Gemini Pro, for instance, basically, when it's doing thinking, one of the first steps it may come up with is, let's restate the user's question in terms of things which I know about. If you think about it, if I'm doing this kind of verifiable reward rollout thing, rewarding stuff where it gets the right answer, a first step which would be encouraged by that would be rewriting it in my own terms. So you can see that naturally these very big models with thinking will actually put themselves on policy as one of the very first things in their thinking stream, except that we don't get to see that. So if you want to use one of the cheaper models, while you may get great results out of the thinking models, you do also want to essentially reveal that thinking and reveal that on-policy conversation, so you can then take that text and start to talk to the smaller models, which are essentially distilled from the large models, so we can talk to them more in terms of what these models have been trained on and hopefully get better results. So at the end of my presentation, I had this quick advert slide for Machine Learning Singapore, which is a meetup that Sam Whitbean and I have been running since 2017. So this meetup has over 7,000 members, and we meet every month. We have a couple of hundred people coming into the Google offices, and we talk about researchy type topics. I just thought I'd leave this slide in here in case anyone is interested. In particular, if you're ever passing through Singapore, which visitors to Asia often are, you'd be very welcome to come along, and please say hi if you do. Okay, so there we have it. That was my DevFest talk. I would expect to go back to more regular YouTube programming, which is kind of more research focused. Please let me know in the comments if you thought this style of video was applicable to you, and whether you find actual value in prompting better or doing fine-tuning better. I'd be happy to talk about DSPY, for instance. On the other hand, I'm also focused on reinforcement learning myself, so that could easily be a topic for further videos, doing deeper dives into reinforcement learning papers, for instance. With that, thank you very much, and see you next time. Cheers.